All right, let's dive into general chemistry. And I mean, we're talking about the fundamental rules that run, well, everything. The air you're breathing, the device you're watching this on, it is all chemistry, all the way down. So let's jump right in. So to get started, let me just throw a weird question at you. What do you think happens when you take an incredibly explosive metal and you mix it with a straight up toxic gas? I mean, we're talking about sodium, a metal that literally blows up if it touches water, and chlorine, that's a poisonous gas. Sounds like a recipe for absolute disaster, right? Well, you get table salts. Yeah, seriously. The same harmless stuff you sprinkle on your food. Now, that's not magic, it's chemistry. And in this explainer, we're going to unpack exactly how these kinds of insane transformations are even possible. So, how does something like that happen? Well, it all starts with the absolute basics, the fundamental building blocks of matter. Everything you can see, everything you are, is just a massive collection of tiny particles called atoms. Okay, so what's an atom made of? You've got a core, right? That's your protons and neutrons. And then buzzing around that core, you have electrons, kind of layered in these shells. But here's the thing. For almost all of chemistry, the only ones we really care about are the ones on the very outside. We call them valence electrons. They are the stars of the show. And if the valence electrons are our stars, then the periodic table, that's our cast of characters. It's this brilliant chart that organizes every type of atom, every element, by how they behave. And you'll notice elements in the same vertical column tend to act kind of similar. Why? Because they have the exact same number of those super important valence electrons. This really drives home the crucial difference between an element and a compound. On their own, you have sodium, the explosive metal, and chlorine, the toxic gas. They have their own pretty dangerous personalities. But when they bond together and become the compound sodium chloride, they create something entirely new, with a completely different and, thankfully, harmless set of properties. Okay, so that brings us to the big question. Why? Why do atoms even bother bonding together in the first place? What is the driving force behind all this? It really all boils down to one of the most fundamental rules of the universe. Everything wants to get to a state of lower energy. A ball is always going to roll downhill, right? It's not going to roll uphill on its own. Well, atoms are exactly the same way. They're always trying to react and form bonds to get to a more stable, more chilled out, lower energy state. So what does low energy look like for an atom? It's simple, a full outer shell of those valence electrons. If you look at the far right of the periodic table, you'll see the noble gases. These guys are the cool kids. They're already stable, their outer shells are full, so they don't really need to react with anyone. Every other element on the table is basically trying to be like them. They're trying to gain, lose, or share electrons to get that perfect, full outer shell. So how do they do it? How do they get that full shell? Well, it all depends on a property called electronegativity. The best way to think about it is like an atomic tug of war. It's literally a measure of how badly an atom wants an electron, how hard it pulls on another atom's electrons. And this one single value is the key to figuring out what kind of bond is going to form. All right, scenario one. What if you have a huge difference in that pulling power? Like with our friends sodium and chlorine. This isn't even a fair fight. Chlorine is so much stronger that it just yanks an electron right off of sodium. No sharing, just straight up theft. Now you've got these charged particles called ions, and their opposite charges make them stick together like magnets. That's an ionic bond. Okay, scenario two. What if the difference in strength is just medium? Neither one is strong enough to just steal an electron, so they agree to share. But, and this is a big but, it's not equal sharing. In a water molecule, for instance, the oxygen atom pulls way harder on the shared electrons than the hydrogens do. So the electrons spend more time hanging out near the oxygen, giving it a little negative charge, and leaving the hydrogens a little positive. This creates poles, which is why we call it a polar covalent bond. And that brings us to our last case. What if the two atoms are basically evenly matched in strength? Well, then they share the electrons pretty much perfectly equally. There's no negative end or positive end, it's just a nice even bond. And because there are no poles, we call it a non-polar covalent bond. So we've covered the super strong bonds that glue atoms together to make molecules. But what happens next? Let's zoom out a bit and look at the weaker forces that decide how all those different molecules interact with each other. And this is where we can finally answer a question you've probably wondered your whole life. Why on earth don't oil and water mix? The answer has everything to do with those forces we were just talking about, and it all comes down to polarity.
It's all about polarity. Remember how we said water is a polar molecule? It has those slightly positive and slightly negative ends, kind of like tiny little magnets. Oil, on the other hand, is made up of long chains that are nonpolar. No charged ends at all.
You know, the old school alchemists actually figured this out centuries ago. They had this Latin saying that pretty much sums up the entire rulebook for mixing things. Similia similibus solventur.
Which, in plain English, just means like dissolves like. It's that simple. Polar stuff dissolves other polar stuff. Those little water magnets are attracted to other polar things, like sugar, and they surround them and pull them apart. But they look at nonpolar oil and they're just not interested. No attraction, so they stay separate. This is exactly how soap works, by the way. It has a polar end that loves water and a nonpolar end that grabs onto grease, acting as the perfect middleman. So let's just quickly rank all these forces. Up at the top, you've got the super strong ones, the bonds that happen inside a molecule, like ionic and covalent bonds. These are the gorilla glue of chemistry. Then, down below, you have the weaker forces that happen between different molecules, things like hydrogen bonds, which are super important for water, and even weaker ones called van der Waals forces. This hierarchy explains so much, like why something is a solid, or a liquid, or a gas. All right, for our last section, let's pull the camera back even further. We've got atoms, we've got bonds, we know how molecules hang out together. Now let's look at the big show, chemical reactions. Why and how do substances actually change from one thing into another? You've basically got two kinds of reactions. Some just happen, spontaneously. We call these exergonic. They release energy. Think of our ball rolling downhill again. It just goes. Then you have other reactions that need a constant push of energy to happen. That's like pushing the ball uphill. Those are endergonic. And chemists have this great measurement called Gibbs free energy that basically tells them which way the ball is going to roll for any given reaction. But hang on, here's where it gets really interesting. Sometimes a reaction can be spontaneous, even if it needs energy from its surroundings. Think about an ice cube melting on a warm day. It's sucking heat out of the room to melt, yet it happens all on its own. How? Because of something called entropy. The universe just has this natural tendency to become more disordered, more chaotic. And a puddle of messy water molecules is way more chaotic than a perfectly ordered ice crystal. That drive towards disorder can be powerful enough to make the reaction happen. Now, a lot of reactions don't just go in one direction. They're reversible. And eventually, they often hit this point called chemical equilibrium. This is a key idea. It doesn't mean everything has stopped, not at all. It just means the forward reaction is happening at the exact same speed as the reverse reaction. So from our perspective, it looks like nothing is changing, but at the molecular level, it's this perfectly balanced, constant dance. And I want to leave you with one final, kind of mind-bending thought. The model of the atom we've been using is super helpful, but the quantum reality is much stranger. Electrons aren't little planets in neat orbits. They're more like blurry clouds of probability. So if atoms are almost entirely empty space and their edges are just these fuzzy probability clouds, what does it even mean to touch something? When your hand touches a table, what are you actually feeling? It's a question that really shows you just how deep this rabbit hole goes.